Hi folks, welcome to part 2 of our Calculus 2 review for our final. Tonight we're going to do some applied problems including volumes of solids and things along those lines. I believe we have some parametric polar curves and maybe a one that involves a Taylor series or something like that. So without further ado, we'll go ahead and get started, and then if you have any questions along the way, please ask them, and you can kind of ask them on the fly too. Just let me know. Put them over in that little chat box and I'm happy to help. So what we're going to start with is the base of a solid having a circular disk with radius 3, and we want to find the volume of the solid if parallel cross sections perpendicular to the base are squares. So what the heck does that mean, first off? Well, we have a circular disk with radius 3, and that's going to be our base, so let's try and draw that first. And we can locate that wherever we want. So if we want a circular disk with radius 3, let's center it at the origin, just make our life a little easier. You don't have to center it at the origin, but I think life will be good if we do that. Oh wow, that's a horrible looking circle this time around. Please bear with me, that is a circle, don't let your eyes fool you. But the main thing that we're going to be dealing with is the equation. So what is the equation of the circle? Since it's centered at the origin, we just have x squared plus y squared, and then that thing should equal the 3 is our radius, so squared. So another way we could write that is x squared plus y squared equals 9. Okay, and one other thing that we can kind of consider is everything popping out of here is a square. So you have a square going right here, and then you'd have a square going right here, and you'd have a square going right here as well. Alright, and this goes down further and further until it comes to some point right about here. And same thing on this side, you have this thing is going around, having squares all the way around until we get to this point right here. And so this actually comes down to that point, and this comes down to that point. So the main thing to take away though when we're working with these is we can actually evaluate that by taking the integral of an area of a cross section with respect to x, or we could do y dy if need be. But we want the area of that cross section. So where the heck is that going to come from? Well, notice the area of a square equals the length of one side squared, right? So that's all we're going to need to work with, but now we need to figure out what is L. As soon as we figure out what that is, then we're good to go. Well, one of the sides of the square, so here's a centerpiece right here, that's one of the sides, or in general we have something like this, right? And so you can have, in this case I'm actually doing, since we're kind of going perpendicular to this y-axis, it might behoove us to actually solve for x and then use a of y dy, and you'll see what I mean by that in just a second. So in this case, the way I have it drawn here, and notice I could have gone the other direction and drawn them up and kind of go slanting to the side the other way, but what happens is we could get x equals plus or minus the square root of 9 minus y squared. That's just by solving for x. And what that means is that this one side right here that I just shaded in red, that is the positive direction. X equals the square root of 9 minus y squared. And this other side would be negative the square root of 9 minus y squared. So when looking at that, if we look at this distance from here to here, right, one way you can think of it is this is x and this is negative x, essentially they're in the same direction. Or you could just take this to be, well, if you get that whole distance, the length equals 2x. Now you might say, oh, just plug that into our area of x dx, but technically we want to adjust for all those values, and so our equation in terms of this x squared plus y squared equals 9, that is the same thing as 2 times the square root of, and this other one was x equals. So 2 times the square root of 9 minus y squared. Okay, so now we're ready for our area equation. So we want area of y dy in this case. And so moving forward from here, and notice I drew it where we were perpendicular to that y-axis. If we draw on perpendicular to the x-axis, then you use a of x dx. You can go either way, it doesn't really matter, you'll still find your answer. But so in this case, we need to figure out our bounds, and I'll put a and b. Okay, so what are our bounds here? Where does the y values range from? Well, notice it goes as low as -3, and it will go as high as +3. So that means we go from -3 to +3 of, so we'd have the length squared, so that would be 2 times the square root of 9 minus y squared, and then we have a dy. So that area equals, we have -3 to 3, and we can pull that 2 on out, and we have just 9 minus, oh, I'm sorry, I said we can pull the 2 on out. It's no longer 2, we had to square that 2, so that becomes a 4 that we can pull out. So 4, and then it goes 9 minus y squared dy. Okay, so the beauty of this thing, we have an even function sitting inside of here, so you can actually even double this and make it a little bit easier of an integral for yourself. So you can go 8, the integral from 0 to 3 of, this would still be 9 minus y squared dy. So this is using the property of that we have an even function sitting inside of there. So this becomes 8, and then we have 9y minus 1/3 y cubed, evaluated at 0 and 3. So the reason why it was nice to plug in and change that is now we can just plug in 0. We don't have to do much work there. So this is 8, and then we have 9 times 3 minus 1/3 times 3 cubed. Okay? Alright, and so I see, can't comment. Yeah, if you do have questions, though, if everything does get back to normal where you can post, please feel free to. If you're having trouble, my apologies. I'm sorry I can't quite fix that. So, but yeah, feel free if you have something and you see it, you want me to go back, just let me know whenever you need to, and then I'll be happy to kind of go back and readdress that too. So moving forward on this part, you get this is 8, and then you have 27 minus 1/3 times 3 cubed is going to be 9. Okay, so you have 8 times 18. So what is that? That's 80 plus 64, so that's what, 144, I believe. And that would be our final answer. So you can kind of see how this rolls around in terms of, and we had some things open to interpretation in how we drew it, right? So you didn't have to center the circle at 0, 0. It just made our work a little bit easier, that's all. So you actually have a lot of options on stuff like this versus other ones where you'll see, well, we have some fixed, here's the equation, you got to work with that. These are a lot more fun that you have some freedom in terms of how you choose to draw it and all that stuff, and where you choose to draw it. But you can come up with the same answer regardless of where you draw it from. So, okay. So moving forward, we'll try another volume one just to make sure we can kind of get this down and go about it and talk about the different methods. So in this case, what do we have happening here? Find the volume of the solid obtained by rotating the region bounded by the curves 3x squared equals y plus 7 and y equals -1 about the x-axis. Ooh, wowzers. So, okay, we have 3x squared equals y plus 7. How is that going to look? Well, when you start to consider this, there's a few different ways to go. You can think of this as an easier way for us to have written this as y equals 3x squared minus 7. And so that'll be a little bit nicer for us in terms of what goes on, because now we know we've shifted down 7 units, right? And granted, we'll have something coming up, but the big one will be y equals -1. So we'll have -1 sitting right here. Here's your -7 sitting right there. And this 3x squared minus 7, we know it goes something like this. And so the area that we're going to revolve is this, and we're going to revolve it around the x-axis. So when we do that, we're going to end up looking at a washer method essentially. And so let me kind of mimic. So this will go on this side. I'll draw in blue what we're revolving around, and we have this shape. This will go to positive 7 here. This would be positive 1. But the one we're going to look at is, so this is y equals negative 1, and this is y equals 3x squared minus 7. And we revolve this around, so you get something that looks like this, but we're taking out, oh, I'm sorry, I put that at the wrong spot in terms of where we wanted to have that cut off. I had it cut off right there. It should be cutting off right here, and same thing with this piece right here. It should be matching in terms of these regards. And so now when I draw that circle, I'll get something like that. I get another piece right here. This thing's going around, and then you get all these little shapes that are kind of going on the inside, where you have this middle interior cylinder taken out every time. So this had a cylinder taken out right there, and so on and so forth. Okay, so now we have this, we have the idea of the image, and we got to figure out, okay, what in the world are we going to do in terms of how we're revolving around that, around the x-axis. So remember, once again, you have actually a couple options. So you can do the ax dx, where the area that you're looking at is of the solid, or the area of a cross section. And then another option would be to use that idea of 2 pi x f of x, the shell method dx. So this is the washer method, or area of a cross section, but we could relate it to a washer method, and this would be the shell method. Okay, so in order for us to do that, we're going to need 2 points, and the 2 points that we're going to need are this one and this one, right here and here. And so how do we get that point? Well, we'd have negative 1 equals 3x squared minus 7. So notice when we add 7 to both sides, we get 6 equals 3x squared. Okay, and then we have 2 equals x squared, and so x equals plus or minus the square root of 2. So that means that the coordinates of this spot would be, right here, would be negative square root of 2, and that means this spot over on this side would be positive square root of 2. So taking a look at this, and we're wanting to rotate around the x-axis, probably our best bet would be something like you could use, well, in this case, since we're revolving around the x-axis, we have a y function in terms of x. Our best bet would probably be to use that washer method. And the reason why, we can always take this down to that point, and then we can revolve it around. So we can always figure out what this radius is. Well, what is that radius there? That's going to be 3x squared minus 7. Okay, so when we revolve that circle around this piece right here, right, we have, okay, so this thing will be 3x squared minus 7, so the area of that cross section, and let me put area 1 of x, will be pi times the 3x squared minus 7, the quantity squared. Okay, and then we have another area, though. We're going to have to consider this area 2 that we're going to have to subtract off. So the area 2 is this distance from here to here. So area 2, notice that's just going to be negative 1 at every single point, so this is just pi times negative 1, the quantity squared. Okay, so keeping that in mind, we're pretty much ready to go. You go negative square root of 2 to positive square root of 2. And now we can pull out the pi since it's in both terms, but we can take the 3x minus 7, the quantity squared, and subtract off the negative 1, the quantity squared. And then we'll take dx. So this is using the washer method. Now, moving forward from here, what do we have? Well, this is pi times the integral from negative square root of 2 to square root of 2. So 3x minus 7, that quantity squared. So notice we'll have, when you square 3x, you're going to get 9x squared. When you take 7 times 3 and then multiply that by another 2, you get 21x, and then another 2 would be 42x. So minus 42x. Then it becomes plus 49, but then we have to subtract off the 1. And then we have a dx. So notice this becomes equal to pi times negative root 2 to root 2. We'll have 9x squared minus 42x plus 48. And notice this once again is an even, well, oh no, it's not actually. We got to be careful. It's not quite an even function because we have that 42x. So I got a little ahead of myself. So we are going to need to plug in all those values. But you could separate it into which functions are even, which functions are odd. That's the nice part, and you'll have things pop out real quick. But so now if we just take an antiderivative, you have pi times, when you take the antiderivative of the first one, you'll get 9 over 3x cubed, so that's just 3x cubed. Okay, so 42 over 2 is 21x squared in the second one. And then the last one will be just 48x. And we're evaluating these from negative root 2 to positive root 2. And hopefully you can start to recognize which ones will go away right away. So you'd have, when you plug in, so you get 3, and then the first case, we'll go root 2 cubed minus negative 2, or negative root 2 cubed. And we can talk about that a little more in depth in a second. And then we have 21x squared. So that goes 21, and then we go root 2 squared minus negative root 2 squared. And then, sorry for the limited space, but then we get plus 48, and then the x values are root 2 minus a negative root 2. Okay, so what happens? Well, in the first case, when you take root 2 and you cube it, you get 2 root 2. And then we get plus another 2 root 2. So notice that makes 4 root 2. So you can write pi times, in our first case, we have 4 root 2 times 3, which we'll handle in just a second, minus, well, the next one you're squaring both of those, so that thing's 0. And then the last piece, plus 48, and then there's 2 of those root 2s, so 48 times 2 root 2. Okay, so pi times, what do we have? We have 12 root 2, and 48 times 2, that makes 96, I believe, root 2. So 96 plus 12 makes 108. So that's pi times 108, and then you have a root 2. And that is our final answer. Okay. Didn't have to go through all the simplifying process. I'm more concerned on, can you organize this and get some nice answer in some format. So even if you have the pluses or minuses, I'm more concerned on the setup on these things. So make sure you can do that, and you'll be in good shape on those. Okay. So now our next one, let's consider this polar curve r equals tangent of 1/2 theta, where 0 is less than or equal to theta, which is less than pi. Okay, so we have a restricted interval. We want to sketch the curve and find the area in the first quadrant that is enclosed by this curve. Okay, so with that in mind, the best way to draw these things is, well, first we can start to draw r up top and theta down below. Okay, and then we'll try and translate this into a polar curve where we do the 0, the pi over 2, and since we're only going to pi, we only need to label that, but you can put 3 pi over 2 and 2 pi and so on and so forth, but that's the whole idea. So in this case, though, we're starting at 0, tangent of 1/2 of 0. Well, tangent, if you recall, in case you struggle with that, that's sine of 1/2 theta over cosine of 1/2 theta. Okay, this is the same thing as tangent of 1/2 theta. But notice if you plug in 0, you get 0 over 1, essentially. So that's just 0. So we're starting at the point 0, 0. Right? Now, we can also go all the way to pi, and kind of, we'll mark that right over here. What happens when we go to pi? Well, think of what tangent is doing. You have tangent usually has these pi over 2. So let me actually kind of draw this. So tangent has this interval where you have pi over 2 and negative pi over 2. This is what the graph looks like. So what have we done when we put a 1/2? Well, basically we've extended that asymptote. So starting from 0 and going on up, we get basically this curve right here. Okay, and so just a little FYI, if we have, when you look at tangent of pi over 4, that thing equals 1. So that's a nice value for us, right? So when would tangent of 1/2 theta equal pi over 4? So if you go 1/2 theta equals pi over 4, that means theta equals pi over 2. So at this pi over 2 mark, you will have the value being 1. Okay? So when we're drawing this thing, here's what happens. So you start at 0, and like the angle, I'll draw this with a dotted line, if I can draw that dotted line somewhat nicely. This would be the angle theta equals pi over 4, right? And so notice that's halfway in between there. So you have to deal with that, and how do we solve that value? Well, what we do know, though, in time is that when you get to pi over 2, you're going to have some radius where you have this distance right here being 1 is our unit. So as we're kind of clicking this around and getting closer and closer, we're getting further and further away, so we're getting up to that value. 1 will be the longest length that we have in that quadrant. So you have something that goes kind of like that. Now what happens? Well, as we get closer and closer to pi, we're getting closer and closer to infinity. So notice we're just growing and growing from here. So as our angle's turning, we're going further and further out, and further out, and further out, and further out, and further out. And this keeps on going, and I'm turning that angle, but what's going to happen is when we approach pi, this thing goes out this way. Okay, so this is all sorts of crazy, right? Now what it wants us to do is find the area of a certain quadrant, right? And so it says sketch the area in the first quadrant, or find the area in the first quadrant. So that's the quadrant we want to work with. Okay, so luckily, though, we know some of those values. In the area of a polar curve, if you have the angles involved, let's call those angles alpha and beta, you can have this be the integral from alpha to beta of 1/2 r squared d theta, whatever the heck that means, right? So now, moving forward from here, what do we have? Well, what are our values in that first quadrant? Well, this should be the integral from 0 to pi over 2. Why pi over 2? Well, we started at 0 as our first angle, and then pi over 2 was our finishing point that finishes it off in the first quadrant. Remember, these are angles, alpha and beta. Okay, so we go from 0 to pi over 2, and then what do we want? Well, we want 1/2 r squared d theta. So r squared, well, that would be tangent squared of 1/2 theta d theta, right? And so now if we were to solve this, what do we need to do? Well, we need to use a u substitution. So you get u equals 1/2 theta. That means du equals 1/2 d theta. And luckily we actually have both of those values. So sometimes you can pull out the constant, but notice there's the 1/2 and there's the d theta. So that's just du. So basically this whole thing becomes, and notice I'm changing the bounds here. I have tangent squared of u du. And as I mentioned, we're going to change the bounds. So how do we do that? Well, we plug in those values. So this value will go into our equation for u, so it'll go in for theta. So plug in here. And so when you plug in 0, you get 1/2 times 0, which is 0. When you plug in pi over 2 into that, so 1/2 times pi over 2, that makes pi over 4. Okay? So now moving forward from here, what do we have? Well, this what gives us a derivative that becomes tangent squared? Well, that's the secant. So we get secant of u, no funny business there, from 0 to pi over 4. All right. And in case you might wonder, okay, what does that look like? Well, that's 1 over cosine. So this is 1 over cosine of pi over 4, in case you don't remember, minus 1 over cosine of 0. Okay? And so cosine of pi over 4, you may recall. So if that means this is pi over 4, that means this angle is also pi over 4. So that goes 1, 1, and square root of 2 right there. Okay? So that means when you go 1 over cosine, so you're going to have, usually cosine of pi over 4 is 1 over square root of 2, but you got to flip it upside down. So that would be just square root of 2 minus, and then 1 over cosine of 0 is just 1. So square root of 2 minus 1. And we can check to make sure this is making sense because the number is positive. Square root of 2 is some number larger than 1, and we're subtracting off 1. So we have a good answer for our final answer as well. Okay. So hopefully that makes sense in terms of how we're drawing it and how we're kind of going about finding the area. The area is going to be the main focal point, along with, obviously you need to know how to draw it when we're doing this. So make sure you're aware of this equation and how it works, like where are your bounds and things like that. We'll do a trickier one in just a little bit. So power series representations, also make sure you know Taylor series and Maclaurin series. Being able to represent all those things is very beneficial. So we'll have this and determine the radius of convergence. So in terms of power series representations, it might be nice for you to know a series of them. You should know for this one what we're going to need is 1 over 1 minus x equals summation n equals 0 to infinity of x to the n. You probably want to know e to the x. You probably want to know sine of x. You probably want to know cosine of x. So like you have summation n equals 0 to infinity. I believe this one's x to the n over n factorial. But you can have them on your cheat sheet and you'll be good to go. Summation n equals 0 to infinity negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial, I believe. This one off the top of my head I think is you take the derivative of the sine, so as long as I got the sine correct, you get negative 1 to the n x to the it goes 2n and then 2n factorial. And you can check out the natural log of 1 plus x. That's also another one that you can work with. And arctangent of x, that's another one that comes into play every now and then. But these are the main ones that I can think off the top of my head that you should have a pretty good handle on. And also being able to integrate stuff involved with this, okay? So you can actually use power series to integrate these, especially when that radius converges is infinite. So in this case though, for f of x, notice we could write that as x to the 5th times, now we need 1 minus x down below, so how do we handle that? Well, we go 1 and then we can factor out a 3, and then that means we have, if we factor out a 3, we have to write this as x squared over 3. Okay, so now what we can do is we can rewrite this as x to the 5th over 3, which we'll handle in just a second. And then we have 1 over 1 minus x squared over 3. So the beautiful thing here is we can now write this as a summation. So this becomes x to the 5th over 3 times the summation n equals 0 to infinity of, well, this should be, we've replaced x with x squared over 3, so this is x squared over 3 raised to the nth power. Okay, well, if you want to simplify this as much as possible or write it in such a way where we can handle it, you can write this as x to the 2n plus 5 power over 3 to the n plus 1 power. Okay, so that's our power series representation. So we're done with that portion. Now for the radius of convergence, the main two that we look for the radius, and then interval we'd have to toss in a little bit extra, but nothing too bad. So radius of convergence is all this problem's asking for. So we can say, okay, well, let's use the ratio test. And from there we have limit as n goes to infinity of a sub n plus 1 over a sub n, which equals, so this becomes x to the 2, and then we have n plus 1 plus 5 over 3 to the n plus 1 plus 1. And then down below for the a sub n, oh, I forgot the, sorry about this, I got limit as n goes to infinity. X to the 2n plus 5. And then we have a 3n plus 1. And notice I didn't put the absolute value in there. I can put it in there, though it's not going to make much of a difference as long as we recognize that x is going to be involved. So in this thing, the limit as n goes to infinity. And then what happens? Well, we get x to the 2n plus 2 plus 5, so that would be x to the 2n plus 7 over x to the 2n plus 5 times, and then we'd have 3 to the n plus 1 be up in the numerator, and 3 to the n plus 2 be in the denominator. And so this thing, notice we can kind of cancel out a whole bunch of stuff, and so we have this equals, we can technically just drop the limit as n goes to infinity with this next step. We have x squared times 1/3, and that should be less than 1. Right? So that means that x, absolute value of x squared, has to be less than 3. Well, we're talking absolute value, so taking the square root, we'll do with the positive square root. So we have absolute value of x is less than the square root of 3. So what does that mean at the end of the day? Well, it means our radius of convergence equals square root of 3. And you can go ahead and even double check and see, okay, what's happening with some of these values is at the endpoints and things like that. But at the end of the day, we got the radius of convergence. That tells us the whole interval, at least from negative root 3 to positive root 3, maybe possibly the endpoints, but the endpoints aren't going to be as important as the interval itself. All those values will correspond to giving us an exact response in terms of this coinciding with that function. But make sure you're aware of all these others going on over here. That'll benefit you greatly when the time comes. Oh, didn't mean to do that. Okay. So now on this next one, sketch the parametric equations x equals t squared, y equals t to the 6th, x equals t cubed, and y equals t to the 9th. Clearly label the curves appropriately. So we'll start with this. And I'm going to intentionally try and throw some things off. So notice, in this case, we get, what would t equal if you take the square root of that? Well, notice you get square root of x equals t, and most of the times we put a plus or minus here, right? Well, let's think about this. If we're squaring t, notice x must be greater than 0. That's going to be important. Okay, so x is greater than 0. And so now what we can do is you can write y equal to the square root of x raised to the 6th power, which is just x cubed. But notice in that first case, you have x greater than 0. So we have this equation is y equals x cubed, where x is greater than 0. So we know what that looks like. Usually we go all the way up, but so now we're just going to start at 0, plug that in, and we get a graph that looks like that. On the other hand, though, this x equals t cubed and y equals t to the 9th, right? If you take the cube root of both sides, you get the cube root of x equals t. Notice we don't have to worry about a plus or minus in this case. Everything's pretty good, hunky-dory there. Okay, so what this means is that y equals the cube root of t raised to the 9th. Well, that's just t cubed. And there are no, or not, sorry, why did I put t? Sorry there. Cube root of x. Let's make sure we get that straight. Cube root of x to the 9th. And so that's just x cubed. But notice in this case there's no restrictions. And so this is why it's important. So this is just y equals x cubed. To see what's happening with those t values when you're plugging them in. What sort of x values do you get? So this graph goes just like that. And notice we're done in terms of drawing our graphs. So distinguishing between the two, that's kind of the tricky part for a lot of people, but you're having the same graph. We got rid of the t parameter, but understanding that one of them has a restriction x greater than 0, and it came from the fact that you're squaring that, you got to think of what values are in the range. Right? That happens from time to time. So all your domains, ranges, and all those things come into play. All right. So now we'll get into the nitty-gritty. So parametric equations, and we're going to do one polar, and hopefully that should be where we're pretty much set in terms of seeing what's going on. So when we consider this asteroid with parametric equations, x equals 5 cosine cubed t and y equals 5 sine cubed t, how the heck do we calculate this thing? Well, in order to do that, we're going to need to find dy dx. Well, in order to do that, we don't have things in terms of x nicely here, so we'll calculate dy dt and divide by dx dt. So what's dy dt? Well, notice we have y equals 5 sine cubed t, so that means this should be 15 sine squared t times the derivative of the inside, which derivative of sine of t is cosine of t. Okay, in the denominator, we'll get 15 cosine squared t. And notice from there, we'll have derivative of cosine of t, which is negative sine of t. Okay, so now we can kind of cross some things off. You have the cosine t will cross off with that square. The sine of t will cross off with that square. The 15s will cancel. And so we're left with sine over cosine and a negative symbol there. So this would be equal to negative tangent of t. Well, that's convenient, right? Because now find the points where the tangent is horizontal. So first off, we got to go dy dx. We need to set that thing equal to 0, but remember that thing is equal to the negative tangent of t. So when does that thing equal 0? Well, you can kind of, well, a couple ways to do it. I'll go back to the unit circle this time. So if you go 0, pi over 2, pi, 3 pi over 2, and 2 pi. And remember that the x value, this is actually where when we get to polar coordinates, the whole idea comes from what I'm writing right now, comes from polar coordinates exactly. If you have a unit circle, your x value is cosine theta, your y value is sine of theta. Right? Usually you can generalize it to x equals r cosine theta, y equals r sine theta, and so on and so forth. But in terms of what we're looking at here, we want this negative tangent in t to be equal to 0. Well, that would be where the sine is equal to 0. So that has to be this point right here, whatever angle that is, and this point right here, and all the repetitions of that. So what this means is t equals 0 plus 2 pi k, where k is an integer, Or the other option is t equals pi plus 2 pi k, where k is an integer. What do I mean by that? Well, it means you can keep on going a full circle around, but luckily we'll see something nice happen with these values. So when you take a look as to what this would work out to be, so we're going to have, let's start with 0. So you get x equals 5 cosine cubed of 0, which is just 5. And then that means your y value is 5 sine cubed of 0, which is equal to 0. So your first coordinate corresponding to this point is 5, 0. So this is when t equals 0. But notice this is sine and cosine. That should be the same value for 2 pi, for 4 pi, for 6 pi, and all those in terms of multiples of 2, some even number times pi. And so the other one, when t equals pi, let's see what happens. You get 5 cosine cubed of, in this case, it's going to be pi. Well, notice that's going to be -1, so this should be equal to -5. And then y will be equal to 5 sine cubed of pi, which equals 0, right? So this is -5, 0. And notice any multiple of pi plus 2 pi k, that's going to be a repeat of the sine and cosine values. So 3 pi, 5 pi, all these will correspond to those same points. So the 2 points where they're horizontal are -5, 0 and 5, 0. And there's no others, right? That's it. And moving forward to the same kind of thing, we want when the tangent line is -1. Well, okay, so this seems a little bit trickier. So we want -1 to equal negative tangent of t, right? So that means that tangent of t equals +1. Okay, so where does that happen? Well, that would happen in 2 spots, in the first and third quadrant, right? Because notice cosine and sine are both they're both positive in this quadrant, so that means you'll get a positive tangent. And same thing, they're both negative in that bottom quadrant, and so that's where you're going to have that value. And you may or may not remember. So one way you could do it is write arc tangent. So t equals arc tangent of 1. But what gives an arc tangent of 1? Let's see. Well, so that means both of the legs are the same, and that means this is the square root of 2. Well, notice we just talked about that. That's going to be pi over 4. So one way to look at it is pi over 4. So you have the triangle here. This is pi over 4. Or the other one would be you have pi over 4 for this angle. Okay? So that means that this full angle from there to there would be pi plus pi over 4, which is 5 pi over 4. So our t values, this would first be pi over 4, but we have t equals pi over 4 plus 2 pi k, or 5 pi over 4 plus 2 pi k, and in both cases where k is an integer. Alright, so what does that mean? Well, now we just have to plug them in. X equals 5 cosine cubed of pi over 4. Well, that's going to be equal to, in that case, it goes 5, and then we have 1 over the square root of 2 cubed. Okay, and then the y value at that corresponding spot would be 5 times 1 over square root of 2 cubed again. So we'll have 5 sine cubed of pi over 4. That's 1 over square root of 2 cubed. And notice if you cube the square root of 2, that's 2 root 2. So another way for us to have written this is 5 over 2 root 2, 5 over 2 root 2. So that's 1 point. And this is when t equals pi over 4. Also, though, any multiple of 2 pi k added to that will also work for the same. So when t equals 5 pi over 4, what happens? Well, our solution, you can plug it in, and then what you'll get is just a negative version of each of those. So you'll get negative 5 over 2 root 2 and negative 5 over 2 root 2. And so that's our other values that we get there. And if you're struggling to see that plugged in, just let me know. But otherwise, you could just write it as arctangent of 1. So you have cosine cubed of arctangent of 1. You're just going back to these values over in the triangle. And then you just got to consider one of them is going to be on the negative for both of sine and cosine. And that's it. And so you're done. So hopefully you see how the derivatives work on the parametric equations. Just take dy dt, dx dt, and that makes things useful. You can kind of bust on through some of those problems a lot quicker. So last but certainly not least, find the area of one leaf of the polar curve r equals 4 cosine of 3 theta. And I want you to recall the area equals this 1/2 from alpha to beta of r squared d theta, right? So what the heck goes on with this one? Well, when we take a look at this one's going to take a little bit more work. We'll start at 0 and kind of go from there. And then we'll try and draw this thing. So 4 cosine of 3 theta, right? So if we knew this is 4 cosine of theta, so we know the height that we're going to get up to is 4, right? And this 3 theta, basically we've compressed it by a factor of 3. So by the time we go and get down here, where should that value be? Well, usually it's pi over 2, but so since we've compressed it by a factor of 3, this is pi over 6. Okay, so then we should reach negative 4. Well, that usually would occur at the value being pi, but since we've compressed it by a factor of 3, this is pi over 3. Okay, so then we come back up, and then where would this next one be? Well, this would be 3 pi over 2, but since we compressed by a factor of 3, I believe that should be pi over 2. And then our next one, when we go back up to make the full cycle on through, whoops, I took that a little too high, sorry about that. What happens? Well, this would usually be 2 pi, right? Because that's the usual period. But so that means this is just 2 pi over 3. So that means we're going to make 3 loops around here by the time we get to 2 pi. So keep that in mind. So what's our next one? We get back to 0. So the next one would be you take 2 pi and add another pi over 2. So that would be 5 pi over 2. So this should be 5 pi over 6, I believe. And then going back down, that should be 3 pi. So this would be just pi right here. Oh, sorry, I made it a little bit more compressed, but we can still get the values. For our next one, notice, so when we take, just to kind of illustrate what's happening here, if you take 3 pi over 2 and you make another loop around, so notice what would that be? This is 4 pi over 2, right? So that makes 7 pi over 2. So that means when we divide that by 3, because we've done that compression, this is 7 pi over 6, right? And so making that next loop around, this would be 4 pi usually, but it's going to be 4 pi over 3 because we've done that compression. Okay, let's keep on keeping on here. So we want to get all the way to 2 pi. Where's the next stop? Well, we got to take 4 pi and add another pi over 2, just to illustrate what that one would be. Notice it says 8 pi over 2, so that makes 9 pi over 2. So that would be 9 pi over 6. And you can kind of see the trend with the pi over 6 as you go pi over 6, 5 pi over 6, 9 pi over 6, right? Back down to that right there. Okay, so now our next one, when we get back down below, what do we have? So this would be 5 pi, I believe. So this is 5 pi over 3. And then we come back right over here. So notice that would be 3 pi over 2 plus 4 pi, which would be 11 pi over 2 usually. But so now we got to make this 11 pi over 6. And then last but certainly not least, we're back to the top again. And so notice this would be 6 pi, which converts all the way back to 2 pi. So wowzers, this thing looks a little crazy. Now how are we going to convert this into something that's polar? Well, first off, let me put the 0, the pi over 2, the pi, the 3 pi over 2, and then we have 2 pi. But that's not going to cut it with our graph. Okay, so notice, what do we have to do? Well, let's divide this thing into pi over 6. So notice to divide into pi over 6, if you go pi over 2 here, right, you've basically divided each quadrant into thirds. So divide that into pi over 6. Let's divide this into thirds. I'm going to do my best to draw this into thirds. So we go here and go here. So this line right here, it's theta equals pi over 6 on both sides. But notice, if I take pi and I add pi over 6, I also get 7 pi over 6. So it's also equal to 7 pi over 6 on both sides. Okay. This one right here, if I take pi over 6 and add another pi over 6, I get theta equals pi over 3. And that means when I draw it over on this side, this is theta equals pi over 3. But it also means I have 4 pi over 3 as well. Because when I add pi to that on the other side, pi plus pi over 3, I get 4 pi over 3. So you have a couple of options there. On the other side, let's do this one. Well, I'll keep it around for now. We got to divide this into thirds as well. So we'll assume we have so if we take pi over 2 plus a pi over 6, I believe that's 2 pi over 3. Okay. And you can also do 3 pi over 2 plus pi over 6. And what will we get? We get 9 pi, so that's 10 pi over 6. So that's 5 pi over 6, I believe. So this one's also 5 pi over 6 as well. So now for this one, we've added pi over 3 to this because it's pi over 6 plus pi over 6. So pi over 2 plus pi over 3, what do we get? So that'd be 5 pi over 6, I believe. Oh wait, did I do that wrong? Hold on. So I got to do pi over 2 plus pi over 6. I got to be a little bit more careful there. Or I'm sorry, 3 pi over 2 plus pi over 6. So that would be 9 pi over 6. So that would equal 10 pi over 6. So I got a little ahead of myself. It isn't 5 pi over 6, it's 5 pi over 3. Big difference. So you have 5 pi over 3 in both of those cases. In this case is where I believe we'll have, so this is just pi over 2 plus pi over 3, and that's where I think we'll get 5 pi over 6. So you get 5 pi over 6 in that area, and then 5 pi over 6 in this area. Okay, so now what do we have going on from here? Well, moving forward from that spot, remember we can take 3 pi over 2, add pi over 3 to that. So if I take 3 pi over 2, I'll actually write it out. 3 pi over 2 plus pi over 3. So get a common denominator, that would be 9 pi over 6 plus 2 pi over 6. And so this should be 11 pi over 6. And hopefully we'll see all the angles kind of corresponding to what we have up above listed here. Okay. So, where do we go from this spot? So now I'll draw this with a dark blue. Alright, we want to start this thing at 4. So we'll say this distance right here is 4 units long. So basically I can take this circle so assume I'm making a circle, because 4 is the furthest we can get. So when we take a look at this, we can actually mark a whole bunch of spots where it's 4. So you have 4, then you have 2 pi over 3 is 4, right? So then you also have, what's another one? 4 pi over, so here, I'll mark them up here. 2 pi over 3, and then 4 pi over 3 are 4. So where's 4 pi over 3? So right here. These will be the spots where we're going to hit 4, right? But that's not the only spot. So here's where it gets a little bit tricky. When you go to pi over 3, right, you're going to get negative 4, right? So pi over 3, you flect over to the other side, and notice that's the same as 4 pi over 3. So we'll have to check that out and kind of see what happens. Same thing when we go to pi. Notice we get negative 4. So that takes pi is this angle, but we reflect over to the other side because it's negative. And then the same thing for 5 pi over 3. So we go to 5 pi over 3, but we reflect over to the other quadrant that's opposite on this line, so that would be negative 4 over there. Okay, so we got all the 4's and negative 4's marked. So everything else is going to stay inside this blue circle. Now how do we draw it from here? Well, let's start with from this section. So we want to go from 4, from the coordinate where we have 0 for that theta, and then 4 for that radius, all the way to pi over 6 for the theta, and 0 for the radius. Well, so notice that pi over 6 will go back to, if it's 0, we're going to go there. And so as we're kind of moving on up, we're getting closer and closer to 0, so you get something like that. Okay, so now where do we go? Well, from pi over 6 to pi over 3, so when we're in this range, let me mark that real quick in orange. So when we're in this range right in here, right, I need to reflect over to this quadrant is what's happening. Okay, so what happens is we're going to go all the way back to when we hit pi over 3, we're going to be at this 4 on this side. So we're basically just repeating this process because that graph kind of mimics itself. So now we've drawn this portion. Okay, what about from the pi over 3 to the pi over 2 right here? So this position. Well, notice what happens is we're going back to 0 once again. So this portion is just basically taking this graph. We're still in the negative version, and we're back to 0 once again. So notice how we're going thus far. Whoops. Did not mean to get that. Just want to make sure we can see this. So, so far we're so good in terms of what's going on. Now, from pi over 2, we're back positive again, and we want to go to 2 pi over 3, which is right in this position again at 4. So we want to try and swing that back up in this positive direction. So we get this for that piece, and then going back down, we're going to go back down to 0 once we hit 5 pi over 6. So we're going to get this shape right here, staying within that angle. So now a little more interesting, what happens when we go from 5 pi over 6 to pi? Well, so for this branch, from 5 pi over 6 to pi, we're over back on the opposite quadrant, like going diagonally. So that puts us back from here, and we should reach -4, which becomes the 4 on the 0 angle. So we get something that looks like this for that portion. Okay, so notice so far we have this little fan with 3 blades essentially. Okay, a lot of symmetry going on here as well. So now from pi to 7 pi over 6, so we're in this quadrant right here, but notice that would reflect, since we're negative, we're going to go back up into here. So pi to 7 pi over 6, oh wait, it's the same graph as what we started with, because it's just the negative version of that. And the same thing happens, so now from 7 pi over 6 to 4 pi over 3, we're retracing this curve right here, right? And from 4 pi over 3 to 9 pi over 6, or another way to write 9 pi over 6, by the way, would just be 3 pi over 2, right? Notice we're retracing this curve, okay? From 3 pi over 2 to 5 pi over 3, notice we're going to be in the negative version, so we're back in this quadrant. So we're just retracing this curve. And then from that 5 pi over 3 to 11 pi over 6, we're retracing this version. And last but certainly not least, from 11 pi over 6 to 2 pi, we're finally back in the quadrant here, and we can retrace this version. So we've basically retraced this the second time by going all the way to 2 pi. So, but this is our graph, right? And so notice we have 3 little fan blades. That's good, okay? And we want to find the area of one leaf, right? So some people call these leaves, or this would be a 3 rose petal, or whatnot, 3-leaved rose petal or something like that. Other names for it, so you'll see all the way throughout. Now, the easiest way for us to do this, though, is when you think about it, we can just take this area right here and multiply by 2. Okay, why is that kind of nice for us? Well, notice that area corresponds to our starting point 0, and we went to pi over 6. So what we can do is we can take the area of the one leaf to be 1/2 times 2, because we're doubling this value, from 0 to pi over 6. Now, it didn't have to be pi over 6. We had other options, right? You could have done pi over 6, for example, to pi over 2. That would also do it, right? So you actually have all sorts of options as long as the fan blade's continuous, essentially, there. And then we want to do r squared d theta. So this would be 4 cosine of 3 theta. We want to square that thing, d theta. Now we have a trig integral, right? So, and notice the 1/2 and 2, they go away. So you get 0, pi over 6, and then we have 16 cosine squared 3 theta d theta, which you can change that using the trig integral properties. This is 0 to pi over 6. We can write this as 16 times 1/2 1 plus cosine. Usually you double that angle, so instead of 3 theta, we're going to have 6 theta. And then we want to toss in, that closes off that one, that closes off this one, so d theta. So this makes 8 times the integral from 0 to pi over 6 of just 1 plus cosine of 6 theta d theta. So the beautiful thing here, we can take this antiderivative. It's not too bad. So this is 8 times theta plus the antiderivative of cosine 6 theta would be sine of 6 theta times 1/6. So, or I'll just write it as 1/6 sine of 6 theta, evaluated at 0 and pi over 6. Okay, so let's see what this thing finishes out to be. So this thing becomes 8 times, well, it goes pi over 6 minus 0 plus 1/6. Then we got sine of 6 times pi over 6 minus sine of, well, that's just going to be 0 there. Okay, I don't know much, but I do know that sine of 0, this thing is 0. And sine of 6 pi over 6, that's just sine of pi, so that thing equals 0. So that whole business is gone. And so what we're left with is just 8 pi over 6, which equals 4 pi over 3. And that's our final answer. And if you want to expand it even further, another place you can go with this, so say you wanted the area of all the rose petals, right? Then you just multiply this by 3. You take 4 pi over 3 times 3, so 4 pi would be the area of all the rose petals that is enclosed right there. So you can get that answer really quick. So hopefully that makes sense in how some of this works. If you have any other questions in terms of what you're doing, make sure to check out Taylor's series and stuff like that. I know we did a few broadcasts on that, but make sure I didn't spend as much time on that, mostly the parametric and polar, because we haven't seen that. But if you do have any other questions, please let me know. I'm happy to answer them along the way. And best of luck to you on the upcoming final. Have a good one.